Hello everyone, we're going to continue our discussion on pinchas. So after we discuss member stiffness relation in the local coordinate system, let us discuss member stiffness relation in the global coordinate system. So by using the member stiffness relation in the local coordinate system from the previous discussion and the transformation relation also from the previous section that we discussed, we can now establish the stiffness relation for members in the global coordinate system. First, we have to substitute the local stiffness relation Q is equal to K times U into the transformation relation. F is equal to the transpose of transformation matrix multiplied to Q, which is our member and this forces in the local coordinate system, and we obtain this equation. F is equal to the transpose of transformation matrix multiplied to member and forces in the local coordinate system, or simply this is the equivalent equation. Then by substituting the displacement transformation relations, U is equal to T times V, we determine that the desired relationship between the member and forces F and M displacement V in the global coordinate system can be obtained by this equation. Member and forces in the global coordinate system is equal to the transpose of transformation matrix multiplied to stiffness coefficient in the local coordinate system multiplied to transformation matrix times member and displacement in the global coordinate system. Or simply, this expression can be simplified as F is equal to capital K times V. This is member and forces in the global coordinate system, which is equivalent to stiffness coefficient in the global coordinate system multiplied to end displacement in the global coordinate system. Our capital K, which has our stiffness matrix in the global coordinate system, is equivalent to this expression. So we need the value for cosine theta and sine theta using the equations that we have discussed in the previous discussion. Of course, you will have to know the value for modulus of elasticity, the area, and the length for each member. And in matrix form, if we try to simplify this one, this is now the simplified form of our member stiffness matrix in the global coordinate system. So we will be using this equation. So let us have an example problem. By using the member stiffness relation in the global coordinate system, this expression capital F is equal to capital K times V, or simply member and forces in the global coordinate system, is equal to stiffness matrix in the global coordinate system multiplied to end displacement in the global coordinate system. So this is our actual thrust. We are given with some parameters, and we are also given with end displacement in the global coordinate system for member 2. So we have V1, which is 0.75 inch, this of 2 is 0, this of 3 is 1.5 inches, this of 4 is negative 2 inches. So we're going to utilize the end displacement in the global coordinate system for member 2 to solve for end forces in the global coordinate system. But before we can solve that one, we have to know the value for capital K, our stiffness coefficient in the global coordinate system. Using the equation that was introduced a while ago, we simply have to find the value for cosine theta and sine theta, and the value for E, A, and L for member 2, then you simplify, and you have now this expression. Once you have simplified this one, this will be multiplied to member and displacement in the global coordinate system so that we can obtain our member and forces for member 2 in the global coordinate system. If we try to simplify this one for operations of matrices, we obtain now our value, which is 345, 460, negative 345, negative 460 kips for F sub 1, F sub 2, F sub 3, F sub 4 respectively for member 2. So that is the unknown data, or the unknown required data for the sample problem that was illustrated for this member stiffness relation in the global coordinate system. So that ends for the